So here, what I am going to present, what new I am going to present, this will be more or less like a tutorial approach to make you understand how what is discrete time sliding mode control, how we are doing that analysis in discrete time mode control, and some advances I will also point, which can motivate you to some research direction as well. So those advances I had pursued with inspiration from my supervisor, Mr. Bandapathy, and we got some good new results, and that can also be further taken forward. So what I will talk about motivation. So already some motivation has been covered. I think Dr. Phillips covered a lot of motivation. That he covered is a lot more expensive than what I'm going to cover in one short slide. So that is a motivation to discrete time sliding mode control, and some early attempts what were made in discrete time sliding mode control. What are the new properties that we found discrete time sliding mode control which are different than the continuous time control? So that warrants an investigation. Right? So why we want to do an investigation in discrete time sliding mode control if it does not give us any new property? What are the properties we are getting in continuous sliding mode control? The properties become different. That's why the investigation is warranted. So those new properties. What are those new properties? Then we have to quickly go into the surface design. It is almost similar to how it investigate continuous time, and the discrete time fixing laws and how they are analyzed. Then the concept of relative degree is introduced in discrete time. And then we will see the advances that what happens if we increase the relative degree to arbitrary relative degree, what are the results, what is the performance, these things we will see. So let us have a quick motivation here. As it has been discussed throughout the day, that have a continuous plant, but our control computation is in discrete time. So there is a clock that governs everything. So all the computation happens at the tick of the clock. So the sampling happens at the tick of the clock. The control computation happens at the tick of the clock. This signal is delivered to the actuator only after the tick of the clock. So this clock governs everything. So all this entire thing is in discrete time. Only the plant is in continuous time. So what was happening is that we developed controllers which are continuous time controllers, but when we apply it in this approach, it got discretized. The control computation got discretized, and people were happy to just apply that same thing, and were thinking that if I have a small enough computation time, then whatever I have, the properties I have found in theory, that would still hold when I am applying that the same in this sort of a discretized architecture. And also, but that is not true. So we will see shortly. So the first problem is that we have a digital implementation of control, so the continuous control cannot get applied. The second motivation is that unrealistic demand from continuous SMC design. So this is specific to SMC. So as you had already seen that SMC has this discontinuity, so the switching function is there, and that cannot be implemented in the actuators. So that is very unrealistic demand from the continuous SMC that we cannot really apply that sort of an actuation that is demanded from this, that high frequency switching, infinite frequency thing to talk about the theoretical sliding mode control. That cannot be applied. So that is unrealistic demand. What are the changes that we observe when we did this sort of a discretization? Then we saw that the signal function definition that was proposed in continuous time SMC design, in discrete time SMC design, the same definition is not there. That changes. The interreachability concept is no longer there. The finite time convergence of sliding variable in most cases does not happen. It may happen in very specific cases, and sliding surface design changes slightly just because of the whole idea of continuous and discrete time. And the reaching laws change. The estimation that we can do with continuous time controllers, that sometimes we can do with this. So it is not just a simple extension, that is the underlying thing. So we need a new investigation. So how does this investigations happen? We'll see shortly. But what is the fundamental difference that happens? The fundamental difference that happens is that the sliding variable never really hits the sliding surface with the switching reaching law. So the switching reaching law is fundamental in the continuous time sliding mode control. You all know about S dot equal to minus S. From here everything starts. So then there are some modifications also. So that S dot equal to minus A sine S. If you just simply discretize it, this is the equation that is coming out. So the system is actually following this sort of a equation, this sort of a dynamics. So you can see that where I am going. So assume some positive sk. Then you see that at every step, you are basically the value of this sk is getting decreased by tau in the sampling time. Tau in the sampling time, your gain. So every instant of time, whatever my value is, present value is, I am getting it decremented by tau. So when can sk become 0? It can become 0, but only for a careful selection of k, depending on the initial condition of s. So you have to know what is s0. Then you can calculate, so how much I have to move, what is my sampling time, and then I can calculate some k. So every time I can. So in that way, maybe very carefully, and it will depend on s0. So that can happen maybe, but it is in general it does not hold. So and also there is effect of disturbance and uncertainty. So if there is any disturbance and uncertainty, we will not know exactly where the value is going. So sk minus tau k will not be taken. It may be something different. So we don't know where the value is. Then another thing that the signum function definition that was there in continuous time, now discrete time, you have to have some value. When you are computing at x equal to 0, you have to give some value of the sign function. You cannot say that it can take any value. So what would be that? The computer will ask because it needs to give up. So we can have the definition changes here that we can fix that. Sliding surface design, you would appreciate that what is the sliding surface design for? At least the LTI systems, we understand that the reduced order dynamics we need to stabilize, and that stabilization for continuous time system will happen if we place the poles in the length of thing, and for discrete time system that stabilization will happen if we can place the poles inside the unit circle. So this is how it changes, but the idea of stabilization is the same. So with this different new properties or differences that we observe from continuous to discrete time, how the evolution happened, how the theory got laid down. So the first attempt was made by Indo-French. He proposed the reaching law, and this reaching law, you can see this is simply a discretization of the continuous time reaching condition. Continuous time reaching condition was s dot s less than minus eta mod s, but that was the eta reaching law. But even if you keep s dot s less than 0, at least you can guarantee asymptotic convergence to s equal to 0. Here you see simply that s dot is discretized and you have this sk plus 1 minus sk and sk less than 0. Now you see the remarkable thing that s dot s less than 0 guarantees asymptotic convergence, but simply discretizing it does not guarantee, because it can lead to a condition of divergence while crossing. So you see that you can still have the mod of sk plus 1 greater than sk when the sign changes, and still this inequality will hold. So only this holding this condition does not guarantee that when I am crossing, I am not having my value sk plus 1 value more than s. If I am having that, that means what? I was trying to reduce my sk value. This is my object. This is my object. I want to make sk lesser and lesser. But as I am crossing, there may be a condition that my sk value becomes more. Still, this inequality will hold. So it is not simply a discretization that will work. So then Tartuk, he simply proposed. So he just simply proposed what is required. What is required is that the mod of sk plus 1 should be less than mod of sk. At every instant, my value, my sliding variable value must be lesser than the previous value in magnitude. So even if I am crossing the s equal to 0, crossing the surface, I am not crossing over. I am not crossing beyond the value that I was holding previously. So there the divergence problem was eliminated if I am able to satisfy this condition. The same condition was proposed in terms of Lyapunov function in this way. But one problem here is that by looking at this, it seems that always my sk will be less than sk plus 1 will be less than sk. So I will reach 0. It seems like that by looking at this condition. So even if I reach 0, this condition holds. But even if I don't reach 0, then also this condition may be holding. But I am still not reaching 0. Okay. And the phenomenon that we observed already is that I will not reach 0. So where I will go? What is the minimum value where I can go? That is not revealed by this condition. That has to be revealed by further analysis. So that was not shown here. Then the Gauss reaching law came where that analysis was made. So how close we can reach to 0. Before that, let us just tally down what are the new properties that were discovered by this discussion so far. That the 0 crossover of the sliding variable happens. It was not happening in the continuous time case. So continuous time case, you hit 0 and you stay. Here you have a 0 crossover. So when we have a 0 crossover, what best we can achieve? The best that we can achieve is that the sliding variable remains bounded in an ultimate band about the sliding circle. So we may say that okay, I am unable to I have to cross 0, but let me restrict the sliding variable or the system trajectory in such a way that the sliding variable is within an ultimate band around. So this is the best that I can do, and let us try to do that. If I am allowing this, then automatically the invariance to uncertainty is lost, because the invariance to uncertainty is the property that appears when we are sliding on the surface, not beyond that. When we are restricted on the surface, only then the invariance to uncertainties are there. But we can still have robustness. So the robustness to uncertainties can still be held if I am within some band. So even if there is disturbance, I am not going too much away. So at least the bounded stability can be proposed. So Gauss proposed the reaching law the first time. So previous things were conditions which needed to be made, but they were not really dynamics which were suggested. So Gauss suggested a dynamics which the sliding variable must follow, and following these dynamics, it would satisfy all the properties that we expect from a discrete time setting method. So this is the dynamics that he proposed, and you still see that this dynamics is not novel in the way it is not a new design from the discrete time sense, but it is simply a discretization of the reaching law which was already there in continuous time. The proportional plus switching reaching law which was already there in continuous time, it is simply a discretization of that. So that it is a direct discretization. And this thing 1 minus 2 tau is between 0 and 1, and k tau is greater than 0. Tau being the sampling time. Ensures monotonic convergence towards s equal to 0. So this doesn't have the uncertainty at this moment, but let us simply look at it and you will appreciate that it is having monotonic convergence towards s equal to 0. How? Because at every instant you see this sk value, whatever is the sk value, it is becoming a fraction of that. Additionally, some decrement is happening. So it is, if you consider from the positive side, the value slowly decreasing, coming towards it. If you consider it from the negative side, you will see the values continuously increasing, going towards it. So there is monotonic convergence of the magnitude of the sliding variable towards. So that monotonic convergence is ensured by this reaching law. Further things that has to be ensured, Gauss proposed that so we have to cross the 0 line, but Gauss said that if we cross the 0 line, it has to, for the first time, it has to be crossed at every sample. Every successive step, it needs to be crossed. So recrossing must happen. And we said that the size of each successive zigzagging step is non-increasing. That means it can decrease or it can remain constant, but it cannot increase. So as soon as the crossing starts happening, it can keep on decreasing, but it will never increase. That is what he is saying. The size of each successive zigzagging step is non-increasing, and the trajectory stays within a specified band. Finally, there will be a band within which the trajectory will stay. If these two are satisfied, then it is sliding in terms of tau. It is, and this is specifically mentioned, given a name, that is quasi-sliding motion. Quasi-sliding motion should respect this property as per Gao. So Gao was the first who proposed this thing. So he said that we can call this quasi-sliding motion, and this quasi-sliding motion must respect this property. And he showed that the proposed reaching law respects this property. How that can be shown? Very easy to show. Already we showed that it is monotonically converging, and here the band is calculated. So for the case where we don't have any disturbance, then what we see is that in the steady state, when we are crossing and recrossing, the value would be same, and that value can be assumed to be delta. So if you put Sk plus 1 as delta, Sk also as delta, then you can calculate what is the delta, and that delta can be calculated, and that is, it comes in relation to the parameters of the reaching. To set the parameters k, q, tau is already known, so you will be able to evaluate what is your delta, and this is the quasi-sliding mode band within which the trajectory will stay. That can be evaluated. Of course, this analysis does not take care of the disturbances. If we take care of the disturbances, then we can again analyze, and we see the same properties hold if we maintain the parameters we listed. So this Pm, what is this Pm? Pm is the maximum magnitude that dk can go. dk is the uncertainty, and it is bounded by Pm. We simply add this Pm with theta, and then the same controller parameter ranges that were proposed can still be proposed, and it will maintain the properties that tau requires for its discrete time sliding mode, for the quasi-sliding mode. So let us see how it holds. So for the quasi-sliding mode, the zigzag motion, one thing you just appreciate that monotonic convergence is still guaranteed. Since this value covers whatever value it can have. Suppose you are starting from the positive side. This can take maximum dm, but still this value will be more than dm. So effectively a negative thing is there. So you are still decreasing. The monotonic convergence is still there. Now we have to see that the zigzag motion is there in spite of the uncertainty. How we can see that? To see the zigzag motion, we have to go to Sk plus 2, and we have to show that the sign of Sk plus 2 is opposite to the sign of Sk plus 1 and same as the sign of Sk. That means the zigzag motion is happening. Okay. So we note that Sk plus 2 is this. So you can simply extend the take a step forward, the reaching law that is proposed Sk plus 1 something. So you make it Sk plus 2, then you have 1 minus 2 tau Sk plus 1, and this is sin Sk plus 1, dk plus 1. Then you put the Sk plus 1 back here. Put it back here, and you need that the sign of Sk and sign of Sk plus 2 should be same. So we can assume that the sign of Sk is 1. So we start from the positive direction. If we start from the positive direction, then this is the analysis, this is the style of analysis we do in discrete time sliding mode control, that we take the worst case scenario. We see that what is the worst value of Sk plus 2 that can be there. Worst value in the sense that I want it to be positive. So I make it worst. I make the right hand side minimum. What is the least value it can take? What is the least value the right hand side can take? If that least value is also greater than 0, then other values that it can take will always be greater than. That is the worst case analysis. So what we do here, this side we see sin Sk is 1, here we have an Sk, and here we have dk. So what is the worst case value of dk? In this case, we have to take minimum. So dk is minus dm, dk plus 1 is also minus. What is this value we can take? So that right hand side becomes minimum, it has to be taken as 0. If we put it 0, it is the least value it can take. So then what we have is q tau k tau plus dm minus 1 minus q tau k minus. That has to be greater than 0. And that condition yields this sort of an inequality. So if we maintain this inequality, that will guarantee the zigzag motion. To maintain this inequality, that will guarantee the zigzag. So the zigzag motion, which was required by the idea of quasi-sliding mode as per Gao, is maintained, we put the parameters like this. What is the band that can be calculated? The band can also now be calculated. Again, the extreme case or the worst case analysis has to be done in this case. So we see that we cross and recross, right? So what is the maximum value that we can cross to? If we want that maximum value, then we have to, supposing that sk is less than 0, so from the negative side I am crossing to the positive side, so I can put this as delta, that is the maximum value, and it will be maximum if from the negative side, what is the maximum value I can put here? 0. Again it is 0, not something negative. Okay, so again this term collapses, and here in this term is negative, so this becomes positive, and this term, what is the extreme case, is again plus. Okay, so the delta becomes 2dm plus delta, and I can write down the dm from this inequality here, and I will get the delta in terms of only the parameters that I have to, having an upper bound, only the parameters of the reaching law that I have to. Okay, and obviously some things to note here is that delta is more than 2 times the bound of the disturbance. So there is something you can something maybe raising in your mind that okay, I know that I cannot come to 0 and I have a disturbance dm, so maybe it is good that I can stay within a band which is dm, because ideally I should be at 0, but now there is a disturbance which is dm, so I can allow till dm, but here I have to allow till 2dm plus data, more than 2. So obviously there is a question that maybe make better. There may be a possibility to make this better. So that question was there in other researchers' mind as well, and these are the questions. Do we really need the zigzagging motion? So Gauss said that for the sliding mode, let us define in this way. We have a zigzagging motion and it will be within a band. If we want to make it within a band, why the zigzagging motion is needed? When without the zigzagging motion, we can keep it within a band, and that making it within a band is sufficient for us. Now we cannot maintain sliding on the surface, but we can restrict the system within a band, the sliding variable within a band. That should be enough. Why additional constraint of having zigzag motion? Maybe there is a possibility to arrive at a lower band if we remove this zigzagging motion. Do we really need the signum function? Some other researchers question this. We really need the signum function. What purpose it is serving now? In continuous time, we understand the signum functions have a purpose to serve. But here, we are not able to guarantee the sliding on the surface in any case. So what is the purpose the signum function is serving? Then, should we not focus on techniques which guarantee sliding motion? Maybe there are techniques which can guarantee sliding motion, and we have drifted from that real notion, because what we are trying is direct discretization of the proportional plus infinity. That was the problem here, because we are trying the direct discretization. Maybe there are other ways, and new formulation has to be developed. So fresh reaching laws were devised without the continuous time design diagram. This is a reaching law which is not there in continuous time an equivalent, but it is a discrete time reaching law, which is directly saying that sk plus 1 equal to 0. You directly make the next instant of sk sliding variable 0. This is a proposition made by Roorkee, and it reaches the sliding surface from the initial position in 1 time. We may be able to do that. It is like a 8-bit control. The point problem in with these things, as you may appreciate already, that the control energy would be too high if the system starts from very far from the surface. But the sliding is exact in this case. Sliding is exact. The system starts sliding from the very first state, but we have not considered disturbance. When we consider the disturbance, then it cannot slide on the surface, but you can see that the sliding variable will be ultimately bounded by a quasi-sliding mode band delta equal to Tm, because the maximum value that sliding variable can take is Dm. So now that thing we have achieved, that we cannot maintain sliding, but only what is the farthest we can go? we go in Dn, plus minus Dn. Other things that we can see from here is that sliding variable assumes the past instant disturbance value. With the sliding variable, if you plot it, you will be able to see what is the actual disturbance that was affecting the system 1 instant earlier. So you will be able to get a plot of that disturbance plot. Control energy is still too high. It will be still too high. The system starts far away from the sun. However, this is huge improvement in the sense that we have been able to reduce the band quite a lot, more than twice. We have been able to reduce the band from the Gauss reaching law. Another reaching law that was proposed by Bartoshevich is this reaching law, where he simply added an additional term here, which is a a priori known function that has a that has a behavior that we can define, and that behavior is defined in this way that this means that the initial value is same. What does this mean? This means that in the same site that it starts. Let's try to read it. What it says is that if whatever my SD0 is positive or negative, SDK must be the same sign. Only then this can be greater than equal to. And SDK equal to 0 for some k greater than k star. So we have to define some k star at this particular time instant. Till this particular time instant, I will have some SDK which is non-zero, but after this time instant will immediately become 0. And till that time instant, I will be decrementing by more than twice m the value that is present. This is the present value. The next value that I am getting is less than this present value minus 2 dm. More than 2 dm decrement I am doing every step. If I keep on doing like this, at some time there you can imagine there is a band 2 dm band. So I am outside that 2 dm band, I will be inside that 2 dm. They are saying that if I am inside the 2 dm band, immediately make it 0. Whenever I have come inside the 2 dm band, now my SDK will be 0. So in this way, it has been defined. What are the properties here? It converges monotonically in finite time from its initial position SD0 to S0 to 0. This a priori function converges monotonically and in finite time to 0. We can set the a priori function to 0, not the actual sliding variable, but this dummy variable, which is the a priori function. And every time instant, it moves by distance greater than 2d. K star determines how long it takes the system to reach this vicinity of the sliding surface, and control effort is substantially reduced compared to the sweeping law. And when we start sufficiently close to the sliding surface, it becomes same as the sweeping law because we come to the next stage. So for this is one such function which obeys all those properties that were defined. And this function, if you plot, you see that this is linear in terms of k. So you start from somewhere, you have a linear slope to hit 0 at k star, and from there onwards you keep maintaining 0. This is called SPT, the a priori function. So what happens that this particular reaching law in here, this part becomes 0, and from then onwards the actual sliding variable will be bounded by dm. So the design part is very similar. So we can have a regular form, and we can design some linear. So this for an LPI system, and the idea is that you have to make the reduced order system. So for the linear time system, we can have some this coefficient design in such a way that this matrix is having all its eigenvalues within the unit circle. So this reduced order system will be stable. So after we come to the band, so this assumption is that S becomes 0 exact. Then this behavior will be recognized in the reduced order system. However, we are not able to make it exactly 0. So whatever that robustness, whatever is that bound is there, that will be reflected in some way here also. So it will not be exactly asymptotically stable, but the states will also not be exactly coming to 0, but it will be also bound. Control law designs that can happen. So using how we go about the control law. So we have some defined SK, like here we have defined an SK as C transpose XK. So we can have SK plus 1, and from the system dynamics it looks like this, and this has to be equated with the reaching laws that were proposed. If I am able to propose a Roorkee that makes this right hand side same as the right hand side of the reaching laws. That means that this control will generate a dynamics of the sliding variables same as the reaching. So whatever analysis we have done for the reaching law, this way it will behave. The same way this sliding variable will also behave, and it will take the system along with it in the same way. So Gauss reaching law will have this sort of, if you calculate, you will get these controls, these control laws from the different reaching laws. So that was the design in the relative degree 1 with the relative degree 1 reaching laws. Now some new results you will see with higher relative degree sliding variable in discrete time. So what is the relative degree that we need to understand? So the relative degree is the order of delay of the output in which the input you take first. It is simply the delay between the input and the output. So if you remember your transfer function, then transfer function also had a definition of relative degree. The same relative degree. Difference between the denominator order and the numerator order. So that happens because of this order of delay between the output and the input. If you have a relative degree r, that means that sk plus I will be some function of xk for I less than r, and the uk does not appear. Immediately when r so and the uk starts appearing from I greater than equal to r. So uk, then if you further go on taking time delays, then uk plus 1 will appear, then uk plus 2 will appear. Like for an LTI system, this is the example of what is the relative degree. So for this sort of an LTI system, if you do to take a linear surface and you do sk plus 1, then you will see from the system we are getting CTA xk plus uk. If your sk has to be relative degree 1, that means uk must appear in this sk plus 1. So for that, CTB must not be 0, and in the case of this being a matrix, we understand it in this way that CTB must be non-singular, does not have a singular. And in this case, where if it is RD2, so if the sliding variable defined has to be relative degree 2, that means sk plus 1 should be only CTA xk. This uk will not be here. So you see that CTB should be 0, but sk plus 2 if you do, then you will get this expression, and here CTAB must not be 0. In order uk appearing in sk plus 2. So this is how we may be able to define in general that if it is a relative degree R system, then it requires that C transpose a to the power of I minus 1 d to be 0 for all I less than R, and CT a to the power of R minus 1 d not equal. So this is the situation. Now we see the analysis with the relative degree 2 region. First we have a design with the relative degree 1 output. So and this will help us compare with the relative degree 2 output. So you see that here the relative degree 1 sliding variable is defined. So in this way, and this is an identity matrix, so that this comes out. So this is the regular form. So this system is in the regular form. That means here we have 0 and here we have V2, and if we do the multiplication here, we simply get V2. So what we need is V2 not equal to 0, and V2 obviously is not equal to 0 because in the regular form this is a non-singular V2, and V2 is not equal to 0. In this equation, we will have the relativity 1 sliding variable. So when it is sliding, then we have this sort of a relationship between x2 and x1, and with the help of this relationship, the closed loop system or the reduced order system, this system, you put back x2k like minus c x1k, this is the dynamics, and you can easily set your c in such a way, if you have controllable system, you will be able to set your c in such a way that this you will be able to place the poles of this matrix within the unit circuit, and that will guarantee your asymptotic stability of the reduced order system. In the case of RD2 out, we have only CX1K. The IM part is not there. Only CX1, because only then your C transpose B will be 0 if you choose the SK as CX1K only, and there is nothing, no part of x2k coming here. Then C transpose B is 0, and C transpose AB, if you do it, you will see it is coming out as CA12, and this will be this will not be equal to 0. This will not be equal to 0. Why? We'll see there is some argument. You can say that A12 can be 0. So we'll see what is the argument against that. We'll see shortly. But let us now go ahead. What is there? So if with this equation you are sliding, suppose you are able to make the system slide with this sliding variable. What happens when S2k is 0? You have C x1k 0. Now obviously C can be chosen in such a way that it does not have a null space. So your x1k will be 0. So you can choose your C in this way that the kernel is 0. So you have this should be written in set way. So it is a null space. So your x1k is 0. Got it. Now you see what is S2k plus 1. When you see this, you will see that it is C x1k plus 1. And we write that C a11 x1k plus C a12 x2k. And since we are sliding already, this is also 0. That means x2k is minus C a12 inverse C a11 x1k. If I am able to choose my C, already you see that C a12 is non-zero. So this exists, and this means that x1k being 0 makes x2k also. So sk becoming 0, that guaranteed x1k becoming 0, that guarantees x2k also. So what is the result here? The result here is that all the states become 0 at the same instant as the sliding initiates. At the same instant. Previously with RT1, you have to make S0. After that, X0 happens asymptotically, following certain dynamics that you need to design. In this case, as S becomes 0, your X also becomes 0 at the same time. And the only thing that you needed to consider is that this selection of C in such a way that its null space is an empty space. In presence of uncertainty and disturbance, this finite time stability of the states will get reduced to some finite time ultimately bounded stability. Of course, you can appreciate that. So we will be able to convert an ultimate band in finite time. So this is the model in the disturbance, and in the regular form it will come to this, and the same analysis, similar thing you can do, and there will be some band coming up. So that I have not shown here, and I am simply going ahead to know what are the reaching laws, because this is the analysis of the system when it is sliding. This analysis we have to do always at the beginning. When the system is sliding, what is the system doing? We see that when the system is sliding, the states have also become zero. But we have to make the system slide. So how to make the system slide? We have the reaching laws to support us. But the reaching laws were defined for relatively one sliding band. But now we are using relatively two sliding variables, so reaching laws need to be translated to relatively two reaching. This is the relatively one reaching law of proposed by Bartolozzi. It gave us the band D to be calculated further by breaking it down. That D M is norm of E to Fn. This is the calculation coming out. For S, if we simply increase one step here and do the analysis, we will be able to see what is the what is the control input. Some new control law will be there, and this will require my P2K to be this, and that means that the norm of E2, which is the maximum, that means the maximum bound of E2 now can be calculated in this way, and that is CA1 to D1. Finally, we are coming up like you see here. Some non-inequality we have used, and we can separate this out. D2 comes out. D2SM already was D1A. This is CA1 to D1. What does this mean? This means that there is a relationship between the ultimate band found with relatively two reaching law and the ultimate band found with relatively one reach. So let us see what is this relationship saying us. In the parameters C same for both RT1 and RT2, we have kept it same. We will be able to make the D2M less than T1M only when CA12 less than 1. When does this happen? So it gets determined by a combination of C and A1. Now you see that usually you can choose S2K as, so in the case of your relativity 2, the C x1K, the C does not have any meaning for the relativity 2 because you can make it identical. So you can simply choose x1K. In that case, A1 to 2 is the ultimate. Here also you see that what is A1 to? If you look at the system, if it is discretized from a continuous time system, what is A1 to? A1 to is a function of the sampling time. It would be a function of the sampling. In case it is an integrated system, it is exactly the sampling. In case it is an integrated system, it is exactly the sampling. And sampling time, obviously you know, is quite a low value. It is in millisecond or microsecond like that. So it is quite a low value. So obviously this D2M is much less than D1M. This is from the, there was an example system that was used in this paper to show this. The evolution of the sliding variable with RD1 sliding variable and RD2 sliding variable in the same parameter C like this, and you can see very easily that the ultimate band is quite reduced for relatively 2 sliding value, which is proposed as in P. This is the control law. We do not do any analysis on the control side, which is better and which is lesser. Analytical, we do not do any analysis. But for the system that had used the example, you can very easily see that the total control energy for the RD2 is also lesser than RD1. For Gauss reaching law, also we can do similar type of analysis. So with the RD1, we know that, so we have written the Gauss reaching law a bit differently. And you can see alpha, beta, this way we have written rather than 1 minus p tau and k tau. This is also one way you can write it. And if you write it in this way, the relationships between the parameters are like this to ensure crossing recrossing. This is the relationship. And the delta, the ultimate band gets calculated in this. So we will use this formulation of the ultimate band in order to compare with the ultimate band found with the RD1 case and the RD2. In the RD2 case, we have simply extended S2K plus 1 to S2K plus 2, and this is the dynamics that comes out, and whatever is there we add a T2K here. You please note that T2K plus 1 is not, so S2K plus 2 is affected by T2K, not T2K plus 1. And here you can do similar analysis from the system. The control is calculated, but the main thing is that to calculate this control, this is the D2K that I should have, and if I have this as this D2K, what is my D2M? The maximum value or the bound of the uncertainty is this, and this again I can write it as less than equal to CK1 D1. Same thing is coming out, but the D1M and D2M expressions are different because in Bartolini's reaching law the band was exactly D1M and D2M, but here the bands are different. Bands are related to D1M. What are these bands? So, okay, before coming to this band calculation, first thing with the relativity 2 reaching law, we have to show that also monotonically converging to 0 and causing recrossing. These two things we have to show first. So let us see what we can show and how far we can show. So you see that one thing you please consider that we don't have any control over SK plus 1. We don't have any control over SK plus 1 because SK plus 1 will not have the control appearing. That is why it is not related to D1, it is related to 2. SK plus 1 does not have any control appearing on it. So if I start from some initial value S0, where my S1 will go I don't know, but I can know where my S2 will go. I have a control over there. So what we can do is we can show the monotonic decrement of alternate samples at least in this case. That is what has been shown, and this is the lemma that says that if P2 is greater than equal by 1 plus alpha, then if both these are in the same side, the sign is same, then the S2K plus 2 magnitude is strictly smaller than S2K magnitude, or it crosses the hypertrophy. If it is the same side, it will be lesser than S2K, or it may cross the hypertrophy. That is what is said. So, how we can show the proof? It is very simple. So, if we have the sign considerations, we can put that in the reaching law. We get this S2K plus 2, and this will be, if we extremize everything, this will be less than equal to this. So, we have put the maximum value of D2M. So, any other value of S2K plus 2 will be less than this maximum value. But this also has to be less than S2K. So, in that, and this is less than S2K. This is less than S2K because D2 is greater than dpm by 1 plus alpha. Because of that, can be sure that this is less than S2P. Similarly, if you consider from the other side, on the negative side, you will be able to show the similar. These above inequalities conclude that the magnitude of S2K plus 2 will be less than S2K, or it will change the sign. Why I am saying it will change the sign? Because it can be low, but it can also become so coming down, decreasing. It is coming down, but at a certain instant it can also cross over. So the interpretation of this lemma would be like this: that the states xk and xk plus 1 are on the same side of the sliding hyperplane. Then either xk plus 2 is also on the same side of the hyperplane and closer, or it is on the other side of that. And a remark you can very well understand, and that is put as a remark, that there will be some k0 greater than 0, such that for any I less than k0, we will have the signs same, sign of the samples of S same, and for S2K and for S2K0, we will have the sign opposite. So there will be an instant where I will cross over. That is being said. This instant is K0. We really don't know what is that instant, but there will be an instant where we cross. The lemma 2 will suggest that if I cross over first, then I am going to recross. So the zigzag motion will be ensured by the lemma 2. It is saying that it will be ensured if this condition is kept on beta 2. So again, same sort of analysis that if we have the sign to be opposite, sign of Sk plus 1 to be opposite to sign of Sk, then sign of Sk plus 2 will be same as sign Sk. How we prove that? We assume that these two signs are opposite. Then we can write what is Sk plus 2. In the dynamics, we can put these signs, and this will be like this. And here you can see that whatever be the k value, since we have taken beta 2 greater than dpm by 1 minus alpha, then we will get the sign of this same as the sign of this. If this is positive, this part will also remain positive. If this is negative, this part will also remain the negative side. So the signs are same in this case also. That means we are doing crossing recrossing. Okay. This is the interpretation that crossing recrossing happens in every subsequent step. Now one thing we note now, that the condition on lemma 2 covers the condition on lemma 1. This is the condition on lemma 1, the condition to guarantee convergence, and this is the condition on lemma 2, the condition that guarantees crossing recrossing. That means if I simply choose my beta 2 greater than dpm by 1 minus alpha, that is sufficient. This will guarantee convergence as well as crossing. So now it looks something like this. Now let us be again clear that every sample may not be monotonically equal or may not be monotonically converged, but every alternate sample will be monotonically approaching the dilation. And once the surface is crossed for the first time, crossing recrossing happens at each time. So the picture can be like this. So you can see that this is S0, this is S1, S2 can be more than S1, but S2 is obviously less than S. Again, S3 is less than S1. In this way, it will progress, and once it crosses, it will start crossing recrossing, and then it will be inside a band. What is that band? It is now calculated, the band, and the band is calculated in the similar way by extremizing things. So we need S2K plus 2 to be the largest value. For that, what is the largest value of the RHS that put, and there Sk was appearing, that also has been put the largest value delta 2, and this gives us delta 2 value, and that we see would be greater than dpm by 1 minus alpha square, because beta 2 is like. Now how to compare between these two ultimate bands? The ultimate band for delta 2 is this, for delta 1 is this. Both have an inequality. So obviously, it would be, from the engineering perspective, it will be the least ultimate band that I can have. I will try to beat that. So I will just use a multiplier, common multiplier, which is very small maybe. So just greater than 1, so that I am able to satisfy this inequality. And when I do the division, then that multiplier also cancels out and I get this ratio. And this ratio, D2M and D1M relationship already had got. So this ratio gives me that delta 2 by delta 1 will be less than norm of CA12 by 1 plus alpha. So this would be less than delta 1 if CA12 is less than 1 plus alpha. So in previously Bartolozzi teaching law, this less than 1 was required. Now this less than 1 plus alpha is. So this is a much more relaxed condition in that sense. Because some alpha is there to keep some buffer, whatever value we want to maintain. But what we have proved that is important, that the ultimate band in the RD2 case is less than RD1. That we can see in the simulation also. The control law is also less energy for RD3. So I will just quickly finish this. This is for arbitrary relative degree output, and this analysis was done only with the 15 shaping. And we can take a general system of nth order which has a lower Heisenberg form. It will work for that, and we can have the B and the C like this. Then only having the B and C like this will ensure that the relative degree is n. So we are working with a nth order system, and the relative degree is also. How we ensure the finite time stability of the states? So we see that when yk is 0, so yk the output itself is the sliding variable in this case. So yk is C x1k, if it is 0, that means x1k is 0. Then yk plus 1 is, if you just simply see x1k plus 1, you will come from the system like this, and since x1k is 0, yk plus 1 also 0 because it is sliding already. X2k will also be 0. In the same manner, you can proceed and you can show that x3 up to xn everything will be 0. And the kth instant is not k plus 1th instant or something. So that means that for this lower Heisenberg form of systems, if the output is simply your x1k, so you have a relative degree n output now. And if you are able to slide on x1k, that is the output, you are making all the states 0 at the same time. Obviously, in presence of disturbance uncertainty, this finite time stability will be the bounded manner, bounded state. This is actually the first work that we did and it was published in variable structure system conference workshop. And later on, the previous work that I wrote, that was done. So in this case also, I think we calculated the ultimate band for RD1 case using 15 shaping law. For all the cases we use 15 shaping law. RD2 case also we use the 15 shaping law variation of the RD2 case. You can see. So here the delta 2 comes out to be like this. Similarly for RD3 and RDR in general, this is the ERM expression that comes. So we have only calculated the expressions here. We have not compared between the expressions because a lot of different terms are coming. So sometimes depending on, and all terms are depending on system specific terms. So depending on the system, it might be that RD2, RD3 or RD4 might be lesser or greater than RD3. So that analysis has to be done for every system, and many some conditions, one condition after another condition will come. Only the calculation of the ultimate bands are shown, and here I will end. So
long live India and France friendship.